So working on this handout, we came up with this quantity that we think is measuring the tendency of a vector field to flow into or out of any particular point. And you know, this quantity is a function, and it makes sense that it's a function because the tendency of a vector field to flow into or out of a point depends on what point you're talking about. So it makes sense that this is a function of x and y. So let's give this function a name. Since it's measuring the tendency for a vector field to flow away from a point, we should give it a name that makes it sound like something flowing away from a point, and the name that mathematicians came up with is divergence. So for a vector field Mn, the divergence of f will be partial m partial x plus partial n partial y. Right? Now this is easy enough to calculate in any given example. You just crunch the numbers on these partial derivatives. So there's really no mystery to calculating this. The important thing about the divergence is what it tells us. So let's work through a couple examples of calculating some divergence, both visually and computationally using symbols. So for this vector field x comma y, if we calculate the divergence of f, so the partial derivative of x with respect to x is 1. The partial derivative of y with respect to y is 1. And so this is 2. Now since this is a constant, that means that this vector field flows away from every point. And this is actually an example that we looked at in the handout. And we convinced ourselves by looking at different points that yes, this does flow away from every point. On the other hand, if we stick some minus signs in here, so let's calculate the divergence of this vector field, minus x comma minus y. Okay, so the derivative of minus x with respect to x is minus 1. Okay, and now we need the derivative of minus y with respect to y. That's also minus 1, so we get minus 2. Now since this is less than 0, this vector field should be flowing into every point. And you know, this is what the vector field looks like. It does indeed look like it's flowing into every point. At the origin, vectors are pointing towards the origin, so it's clear that the vector field is flowing into the origin. But even for other points, the vectors flowing into the point are more numerous and longer than the vectors flowing out of this point. And so on net, this vector field is flowing into that point, and so the divergence at this point should be negative, and indeed it is, since the divergence is the constant minus 2. Let's look at one more example. How about this example? So for this example, it's much less clear just looking at the formula for this vector field what the divergence ought to be. So let's calculate it. Divergence of f is going to be, so partial derivative of sine x with respect to x, so that's cosine x, plus partial derivative of cosine y with respect to y, that's minus sine y. Okay, and now this genuinely does vary from point to point. Right, so whether this vector field flows into or out of a point really does depend on what point you're talking about. We could go through a long analysis to figure out what regions in the plane, for what regions in the plane is this positive or negative, but let's not do that. Let's just look at a few interesting points on the graph of this vector field. So you can see that there are some points here where the vector field is clearly flowing towards these points. If we look at the scale on this, it looks like this point here might be about, say, pi and pi over 2. So let's see, what is the divergence of f at pi comma pi over 2? If you haven't seen this vertical bar notation, this just means evaluate this function at that point. So we're just plugging in the point pi comma pi over 2 into the function divergence of f. Okay, so we get cosine of our x coordinate, which is pi, minus sine of our y coordinate, which is pi over 2. So cosine of pi is minus 1, minus sine of pi over 2 is 1, so we get minus 2. So yes, at this point the divergence is negative, and so this vector field ought to be flowing into this point, and yes, indeed it is. You can check for these other points Right? You can guess their coordinates based on the scale of this graph. You can check that the divergence does come out to be negative. So how about other points? Well, there are also a few points on this graph where the vector field is clearly pointing away from the point. And I think right here is one of them. So let's look at this point. The coordinates for this point, well, the x-coordinate is clearly 0. The y-coordinate is a little hard to tell. Looks like it's about here. Let's guess that that's pi over 2, or minus pi over 2. Okay, so let's calculate the divergence of f at 0, comma, minus pi over 2. So that's going to be cosine of 0 minus sine of minus pi over 2. So cosine of 0 is 1, minus sine of minus pi over 2 is minus 1. So that comes out to be 2, which is positive, right? So that verifies what we see on the graph, that this vector field is flowing away from this point. Again, you can check for all of the other points where it's clearly flowing away that the divergence is positive, like here and here and here. There are some other points where it's actually hard to tell what's happening, say right here. Some of the vectors are flowing away from this point horizontally, but it's hard to tell what's happening on the y-axis because we can't see the arrows there, but I think that the vectors are flowing in. So let's check at that point what the divergence is. That point looks like it's going to be, well, the x-coordinate is clearly 0, and the y-coordinate looks like it's pi over 2. Okay, so the divergence is going to be cosine of 0 minus sine of pi over 2, and yes, indeed, that is 0, right? 1 minus 1. So that is 0, and that verifies that there is no net flow into or out of this particular point. So, so divergence is straightforward enough to calculate. Of course, in addition to being able to calculate divergence from a formula, right, the reason we care about divergence is because what it tells us, whether a vector field flows in or out. So if we just look at a vector field, we should be able to approximate, just by looking at it, where the divergence is going to be positive and where it's going to be negative, just by thinking where flow is roughly into a point and where flow is roughly out of a point. So for an example, here's a kind of complicated function, and for any function of x and y, its gradient is a vector field, and here's what the gradient of this function looks like. So let's estimate where this gradient, I said where it's positive and negative, but what I meant is where the divergence of this is positive and negative. So for positive divergence, we want to know where, or we want to estimate where does it look like the vector field is flowing away from a point. Well, definitely here, right? The vector field is definitely flowing away from this point. But even over here, the vectors flowing out of this spot are longer than the vectors flowing in. So even over here, it's going to be positive. Same thing over here. The vectors flowing out are longer than the vectors flowing in. And that's true, it looks like roughly in this patch. So the divergence is going to be positive in this patch. On the other hand, over here, there's a point where the vector field is clearly flowing into this point, so the divergence is going to be negative there. At points nearby, like right here, the vectors flowing into this point are longer than the vectors flowing out, so the divergence ought to be negative there. And similarly down here. So just like this left side had a patch where the divergence is positive, it looks like the right-hand side is going to have some patch, looks like maybe the same size, where the divergence is negative. If we actually wanted to know exactly where this divergence is positive and negative, we could actually calculate the gradient and then calculate the divergence of the gradient to see. That would probably give us some messy inequality though, so let's not do that. One final thing about vector fields and divergence is that some vector fields actually have 0 for their divergence, and those vector fields are called incompressible. And the idea behind the name is that if you have a fluid flowing around and you can't compress the fluid, well, if you can't compress it, that means that at any spot, any fluid, whatever rate fluid flows in, it has to flow out at the same rate. Because if it didn't flow out at the same rate, that means you're packing more fluid into this spot than there was to begin with, which means you're compressing it. Well, if you can't compress the fluid, then that's not allowed, and so the divergence has to be 0. So that's the idea behind the name of incompressible. And most vector fields are not compressible, but some vector fields are. So for example, this vector field, if we compute the divergence of x comma minus y, so the partial x is 1 plus, and then the partial derivative of our y coordinate function with respect to y is minus 1, and that's 0. So this particular vector field, it's hard to tell, but this vector field is incompressible. If a fluid flowed with this velocity field, the fluid would not get compressed anywhere, right? Many fluids are incompressible, so vector fields that are incompressible are important in fluid dynamic type situations when you're dealing with incompressible fluids. Water is essentially incompressible. You have to get to very high pressures before water compresses any appreciable amount. Air is actually also relatively incompressible as long as pressures don't change too much. Sort of in your general vicinity, air is more or less incompressible. Of course, on a large scale, air is very compressible because it has different pressures, but on the small scale, most fluids are incompressible.